Hello and welcome back. In our last topic, we introduced basic Kubernetes volume and saw how emptyDir volume can outlive a container restart, which is great for sharing data between sidecars. But what happens if a pod itself dies or it deleted? Our emptyDir is gone forever. This is fine for temporary data, but for our most crucial application, this is fine for a temporary data, but for most critical application, like a database, we need our data to live on far beyond the lifecycle of a pod, node, or even a cluster itself. We need a way to completely decouple the lifecycle of our data from the lifecycle of our cluster resources. This is the responsibility of the persistent volume subsystem. Kubernetes modeled this with two distinct but connected API objects: the persistent volume and persistent volume claim. The core concepts, PV and PVC. Understanding these two objects is the key for all storage in Kubernetes. A persistent volume or PV represents the actual storage device in cluster. This is cluster level resources like a worker node. It's a supply of storage. A PV is an administrator resources. It captures the details of the underlying storage, whether that's an NFS share or a host path or cloud provider storage block. Persistent volume claim, or PVC, is a request for storage made by a user or application. This is a namespace scoped resources like a pod. Its demand for storage. A PVC says, I need 1 gigabyte of storage and I need to be able to write to it. It doesn't know or care how the storage is provided. It just makes the request. Your pod then claims the PVC. Kubernetes' job is to see the pod's claim and bind that PVC to the persistent volume that can satisfy its request. This is a brilliant design. It's abstract the storage away from the application. Your developers who create the pods and PVCs just say, I need 10 gigabyte of storage. You, as administrator, who create the PVs are the one who worries about how to provide that storage. Static vs dynamic provisioning. So where do these persistent volumes come from? There are two ways: static provisioning and dynamic. Static provisioning. This is the manual approach. As an administrator, you pre-provision your storage. You might crave out a directory on NFS server and then you manually create the persistent volume object in Kubernetes that points to that NFS share. The PV then sits there, waiting for a PVC to claim it. Dynamic provisioning. This is a modern, automated approach. Instead of creating PV one by one, administrator create a storage class. Storage class is like a factory of PVs. When a user creates a PVCs that request certain class of storage, like fast SSD, the storage class will automatically and dynamically provision a new PV from the cloud provider, bind it to the PVC and make it available, all in matter of seconds. Dynamic provisioning is the future, but to understand it, you must master the fundamental. So for now, we are going to focus on the static provisioning workflow. So let's switch to the terminal. With static provisioning, our job as administrator is to create the persistent volume object first. kubectl doesn't have imperative create PV command, so we must use a YAML manifest. Let's look at this nginx PV YAML file. So I have my PV here. This is very simple PV. Let's break it down. Metadata name. We are just calling it nginx PV, as you can see here in the metadata name. And then spec capacity storage. We are declaring that this volume has capacity of 1 gigabyte here under the spec and capacity. And spec access mode. This is critical. We are setting it read write once, which means that this volume can be only mounted for reading and writing only by one single node at a time. As you can see, it's here. And the host path, a spec host path, this is our volume type. We are telling Kubernetes that this PV is backed by directory data www on the cluster host node. This is great for learning, but you would never use host path in a real multi-node cluster. Let's create it. kubectl create -f, then pv.yaml. This output is packed with important information. Capacity is 1 gigabyte, as we said. Access mode is RWO, the short for read write once. Status is available. This is the key. It means that our PV is not bound to any claim. It's sitting on its shelf, free and ready to be used. Reclaim policy is retain. This is default and very important, as we will see it in a moment. Now we can use our PVC to claim and persistent volume that we created. So right now I can show you the PVC YAML manifest. Here is our PVC request. The name is Nginx PVC. I'm using access mode read write once, and the resources, I'm asking for 1 GB of resources. And then I'll create a pod, Nginx pod, to use the persistent volume claim. I'm attaching this persistent volume claim Nginx PVC as a web data in volumes, and I'm mounting this web data into the path of user share Nginx HTML. Let's create this. Okay, apply -f pvc.yaml. So as you can see right now, Nginx PVC created, Nginx PV pod created, and Nginx PV service created. Now let's get the PV this time. As you can see, the status is bound. It means that right now this PV is attached to a PVC. Let's get the status of our Nginx. As you can see, Nginx PV pod is running. So we can get the address of our Nginx and then connecting to this pod. As you can see, this is giving me the hello from PV backend Nginx. But let's see the actual file, because we use the host path, so the file should be exist in our host. But first, to get the host, we need to check that which node this pod is running on. So it's running on kube worker 01. We only have one worker in our cluster. So if I'm listing the nodes, you can see that we only have one worker node and one control plane. But if we had more than one worker node, this would be different. The data, if it was scheduling on node worker 02 or 03, then the data would have been exist in that node. So let's connect to the 201, which is our worker, and list file under the data www. As you can see, the index HTML is here. So let's cat the data inside of the index HTML, and this is exactly the data that we're having in our Nginx. Even we can change the file contents here, like let's say we are changing the data on the host path directly, like from PV backend Nginx, and then saying that it's modified. Okay, so let's go back again to the control plane, and now curling the file. As you can see, we are getting this response, hello from the PV backend Nginx and modified in yen. It means that the file is shared between the host and between the container with host path that we used as a PV. And then we use PersistentVolumeClaim to claiming this PV. Let's remove the PV and PVC and what's happened since we had this reclaim policy, retain. So first let's delete -f the PVC. Status is still bound, but soon we should, after terminating of Nginx PV pod. As you can see, the Nginx PV status is released now. It means that it's available to attach to another claim. But let's remove the PV. What happens if we remove the PV, since the reclaim policy is retained? So the PV is also deleted. So let's connect to the worker node again and see is the file still exist in under the data www. As you can see, the index HTML is still exist here. It means that whenever we're deleting the actual PV, the data remains under the provider. If it's hostpath, if it's any provider, the data will be unpacked and remains under the provider. A deep dive on PV configuration options. That K explain PV specs output just show us 3 most important configuration objects for any persistent volume. Let's break them down. Volume mode. The first option is volume mode. This is define how the volume is presented to our pod. So here, as you can see in this configuration, we have block or file system. This file system, this is default. The storage is presented as mounted directory, just like we expected. If the underlying device is a raw block, Kubernetes will format it with the file system first. The block storage or block. This is more advanced option. It presents the storage as new raw block device like dev SDA directly to the pod with no file system. This is great for high performance application like databases that want to manage the raw blocks themselves. So they are not depending on the file operating system to manage the file system for the database, for example. Second one is access mode. This is one you will configure most often. Define how the volume can be mounted and used. The three most important ones are read-write once. The volume can be mounted and read-write by a single node. This is the most common mode for block storage, like AWS EBS volume. Read-only many. The volume can be mounted and read-only by many nodes simultaneously. This is great for sharing data that doesn't change, like a config file. And read-write many, or RWX. The volume can be mounted as a read-write by many nodes simultaneously. This is the most complex and flexible mode, but it's only supported by storage systems that are designed for it, like NFS or other shared networking file systems. Finally, the reclaim policies define what happened to the persistent volume after the persistent volume claim that was bound is to delete it. The first option is retain. This is the default when the PVC is deleted. The PV is released. Its status becomes released, but it's not deleted. The data on the underlying storage is still there, safe. This is the safety first feature. An administrator must manually clean up and delete the PV. Delete. This is policy tell Kubernetes when a PVC is deleted, I want you to also delete the PV and the underlying storage. This is almost always used for dynamically provisioned volume. Recycle. This is deprecated, so you should not use it. So let's go back to the presentation. To recap, the persistent volume is the supply of storage provisioned by an admin. It defines the capacity, the access mode, and the reclaim policy. We have now successfully created a PV and PVC statically. It is setting in our cluster with the status available. In our next topic, we will create the other half of the question, the storage class and dynamic provisioning. Thank you for watching.